Example 1. Part A. If S of t is the position of a moving object in feet and time t is measured in seconds, find the units of the derivative of S of t, also known as the velocity. So remember, there's two different ways we know now to write the derivative. So we could use Newtonian notation, which would be S prime of t, or we could use Leibniz notation, which is the derivative of the dependent variable with respect to the independent variable. So since here S is my dependent variable and t is my independent variable, this particular derivative would be ds dt. So the units here are going to be the units of S, which we said were in feet, over the units of t, which is time, which was measured in seconds. So here, the derivative is going to have the units of feet per second. There's also an interesting relationship here that we should note. This says that if we take the derivative of position, that's called velocity. And velocity is often written with a v. So we can say S prime of t equals v of t. So that means that the units of velocity in this problem would be in feet per second. And that's also the units of the derivative of position. Part B. If the velocity, v of t, of an object has the units found in part A, then what are the units of acceleration, a of t, which is the derivative of velocity? So again, let's start with some notation. So we're looking for the derivative of velocity, which in Leibniz notation would be dv dt here, because v is now our dependent variable. And so here, the units of v say that it's the units that we found in part A. So that's feet per second. So that's just the units of v. Our independent units are going to continue to be time. And since we're going predicated on part A, the independent units have not changed. They're still going to be in seconds. So we get feet per second divided by seconds, which is feet per second squared. So the units of acceleration, or the derivative of velocity, are going to be in feet per second squared. So something new and interesting happened here, where our dependent variable no longer had a single unit, but instead had a rate as its units. So when you have a rate, you can still do it the same way. You're taking the units of the dependent variable, whether it's a single unit or a rate, and you're dividing by the independent units. And here's a little tip. When you have a rate, whatever was in the bottom is always your independent units. So you can just copy that down in the bottom. So you're always going to end up with something squared. Now, just to be really clear about the relationship we have here, we said the derivative of velocity is acceleration. Now, just to sort of give us a glimpse into the future, I want you to notice that when we took the derivative of position, we got velocity, and the derivative of velocity was acceleration, which means that the second derivative of position is acceleration. So if we were to take the derivative 2 times on position, we would end up at acceleration. We haven't talked about the second derivative yet, but in the next section, we'll spend a lot of time talking about it. And we'll circle back to this in chapter 3, this idea about the relationships between position, velocity, and acceleration. Example 2. Use the graph below to A, estimate g prime of 20 using the tangent line, B, find the units of g prime of t. So this is similar to what we've been doing in previous sections, only now we're also concerned about what the units are of our approximation. So if we want to approximate the derivative at 20 using the tangent line, we need to draw in a tangent line that touches at 20. So I've drawn one in to the best of my ability here, and it's in orange. So what you'll notice here is that right at 20, is where we're going to touch. So right about here. And again, if I want to approximate the derivative at 20, I'm looking for the slope of the tangent line. So in order to do the slope of the tangent line, I need to find 2 points that are on the tangent line to approximate the slope. And again, I can pick any 2 points I want that it appears the tangent line is going through. However, I want to try to pick them so that my calculation is as easy as possible. So here, if I look carefully at my tangent line, it looks like it's going to go through the point 16, 0. So the left endpoint right here looks like it goes right through here. And then I'm also going to pick the point 41.5. Again, if those aren't the points you picked, that's okay too. I see the point 32, 1. That would be pretty good. 20 and maybe 0.25 would be okay points. So any 2 points on the line. Once you have the points on your line, we can approximate the derivative at 20 by doing the change in y over the change in x. So remember, our y values are the second values here. So I'm going to do 1.5 minus 0 divided by 40 minus 16. And that's going to give me 0.0625. So now that's part A. I've gotten a slope of the tangent line. It's an approximation because I'm estimating the points. It may not be perfect, but it's pretty close. And now I want to take that number and I want to give it units based on the problem here. So what I want you to notice is that in this graph, the dependent units are in kilograms. So that's what's going to be on the top. And then the independent units is in weeks. So g prime of 20, the derivative at 20, is 0.0625 kilograms per week. So whatever this is increasing by 0.0625 kilograms for every additional week that we go on. So if we went from 20 to 21 weeks, we would expect that whatever this is would gain 0.0625 kilograms. Because again, this is the idea that we're increasing the independent variable by 1 unit. So going from 20 to 21 will increase the dependent value, kilograms, by 0.0625. Example 3. The time for a chemical reaction, T in minutes, is a function of the amount of catalyst present, A, in millimeters. So T equals F of A. We want to interpret the following statements. F of 100 equals 7 and F prime of 50 equals 4. Now, it's very tempting to always turn T into time and to always make that your independent variable. But here we have to be extra careful because I want to point out that my independent variable here is A, and A is in milliliters. And it turns out in this particular example that my dependent variable is time, which is minutes. Now this is unusual. Generally when we have time, it's our independent value. So here we have to be extra careful when we're assigning units and making meaning of our statements. F of 100 equals 7 means here that the 100 is actually in milliliters, which may not be what you had initially thought. But remember that my independent variable A is what I'm plugging in. So I'm talking about what happens when I have 100 milliliters. Now 7 is going to be my time, and 7 is going to be in minutes. Notice here I'm not talking about the derivative. I'm just talking about F of 100 equals 7. So I'm talking about the time for the chemical reaction when 100 milliliters are present. So the time for the reaction is going to be 7 minutes. So when I construct a sentence, I need to make sure I'm talking about 100 milliliters and that the reaction time is 7 minutes. So I could say something like, when 100 milliliters of catalyst is present, the reaction takes 7 minutes. So again, what's important here when I make meaning is that the numbers are attributed with the right units. There's lots of ways we could write this sentence. Now let's look at part B. Now we're talking about the derivative of this function, and we're talking about f prime of 50 equals 4. So again, the 50 is going to be in milliliters, because again, that is my independent variable. So I'm talking about the reaction when I have 50 milliliters of the catalyst present. That's the point that I'm talking about in this particular problem. Now the 4 is the derivative. So here, because I'm doing the derivative, I can use Leibniz notation to think about what the units are going to be. So the derivative of capital T over dA with respect to A. So the derivative of time with respect to milliliters. So here, my T is in minutes, and my independent variable is in milliliters. So the units of 4 are minutes per milliliter. So what does that mean? So that means when I have 50 milliliters of this catalyst, that my reaction is speeding up by 4 minutes per milliliter for every additional milliliter of catalyst that I add. So my sentence could look something like this. When 50 milliliters of catalyst are present, the reaction is speeding up by 4 minutes per milliliter. So what that means is if I were to go from 50 milliliters of catalyst to 51 liters of catalyst, my reaction would speed up by 4 minutes. So by changing the independent variable by 1, it would change the dependent variable by 4. This idea also works in the other direction. So I would know that if I reduced the milliliters of catalyst from 50 to 49, it would then slow down the reaction by 4 minutes because I'd be moving backwards in time. But again, the idea is that we want to take the numbers and attribute the correct units so that we can make meaning and talk about what's happening. And again, just as a reminder, time is not always the independent units. Most of the time it is, but occasionally, in an example like this, we get time as our dependent units. Example 4. The amount of medicine in milligrams found in the bloodstream, C of t, is a function of time t in minutes after taking the drug. We want to interpret the statement C of 35 equals 90. So inside of our function is our independent units, where we said was time in minutes. So this is 35 minutes. And C of t is in milligrams. So this 90 is in milligrams. So I would interpret this statement as 35 minutes after taking some medicine, 90 milligrams of that medicine can be found in the bloodstream. So again, the 35 needs to go with minutes and the 90 needs to go with milligrams. Part B, write the derivative of this function using Leibniz notation. So Leibniz notation says we're going to have the derivative of the dependent variable with respect to the independent variable. So we're going to have dc dt. That's going to help us in part C figure out what the units are going to be. So part C says interpret the statement C prime of 15 equals 7. So remember, the number that we're plugging in is always your independent variable here. So this is going to be in minutes. And the units of our derivative are going to be the units of C over the units of T. So the units of C are in milligrams, and the units of time are in minutes. So the units of 7 are in milligrams per minute. So the statement C prime of 15 says to me that 15 minutes after I've taken some sort of medicine, the amount of medicine in my blood is increasing at 7 milligrams per minute. So what that also tells me is that if I were to go from 15 minutes to 16 minutes, I would expect the amount of medicine in my bloodstream to increase by 7 milligrams. So again, 1 unit increase in the independent variable has a 7 unit increase in the dependent variable according to this derivative.